The way I got started in this, about 1995, I was teaching computers, and sometimes the computer lab would get used by a teacher, and I didn't have anything to do, so I'd wander around in the library since the computer lab was actually in the library. And I'm over in the physics area, and I see this book. And it was this one here called The Dancing Woolly Masters. So I said, well, that doesn't belong in the physics section. Somebody's got that in the wrong spot. Pulled it out and had this picture of these dancing legs on it. And so I looked at the number on the back, and it was according to the number on the back. That's right where it should have been. But I thought, it's a dancing book. They've got it misnumbered. And then I looked down below. I pulled it off the shelf, and I was going to take it up to the counter. I looked at it, and it said, an overview of the new physics. Well, maybe it does belong in this section. And so I opened it up and read the little blurb in the front, and I said, wow, this is fascinating. So I took it up to the counter anyway and checked it out and read it. And by the time I got done, it was unbelievable. It's written by a guy named Gary Zukov. In here, Gary Zukov makes this statement towards the front of his book. Common sense contradictions, in fact, are at the heart of the new physics. Now, when he talks about the new physics, he's referring to quantum physics. They tell us again and again that the world may not be what we think it is. It may be much, much more. Now, there's a guy by the name of Dr. Fritz Schaefer. This guy is at Purdue. He teaches chemistry. And he is the third most cited chemist in the country. Now, the interesting thing about these guys who are at that level, most of them believe in God. They do not believe in evolution. It's only the people who are less educated than they who believe in evolution. If you get enough education and you really understand how the world works, evolution doesn't fly. Einstein made the statement that anybody who believes in evolution doesn't understand the problem, and when we get done here, you'll understand what he was talking about that. But Dr. Schaefer makes this statement. The significance and joy in my science comes in the occasional moments of discovering something new and saying to myself, so that's how God did it. My goal is to understand a little corner of God's plan. And he's talking scientifically, not necessarily theologically. So let me start with a verse that we've all heard. Genesis chapter 1, verse 3 says, and God said, let there be light, and there was light. We're going to shed some light tonight on that verse. Since the early 1800s, experiments were being done with light. All these experiments that were being done concerning light itself were creating major problems for the scientists. They did this for a complete century. One of the first experiments done was by a Thomas Young. He did this in 1803. Problems created by this experiment would not be solved for 100 years. He did it the double slit experiment. This was an unbelievable experiment. It was one of those experiments that happened exactly the way it should have. And that was the problem. And it works on the idea that light waves, as they go out, if they have multiple sources, they will create interference patterns. Anybody who deals with sound understands that. If you're running two speakers like this in a room, if you've been in any auditoriums, you've all run into this situation where one person will say, man, I just couldn't hear today. And the other person says, man, it was too loud for me. Well, the reason that happens is you have, as the waves cross each other, where they cross, they add. So you get the sound level coming from both speakers. But where the waves are going opposite, in fact, let me just draw this. If you have a sound wave, and this could be a light wave also, and if you've got two waves and where you're sitting, they're doing like that, that's called in phase. So you're getting the volume level from both of those speakers. But if you just move over a few feet, you may find that you're sitting in a place where the sound from one speaker is doing this, and the sound from the other speaker is doing that. Now what happens there? They're canceling each other out. And so if you're sitting there, you're going like this, Well, 3 feet away, that person's going like this. So one of the things you can do in an auditorium is if you don't like the sound level, move. Okay? Now, if you're in one of these churches that has a single speaker up here, that won't work because you don't have these issues. But when you have multiple speakers, you start getting these kind of issues. Well, light can do the same thing. And so what he did is he had a board like this, and had a light source over here that was sending out the light. And here he had this board. And in the board, he had 2 slits. And so he would shine the light at that board, and you get a pattern over here. Some of you have done this thing. You've ever done like the pinhole camera, where you put a hole in a piece of paper, and then you hold it up, and you kind of get an image? Kind of the same type of thing, only it's these slits. So if he covered one of those slits up so the light could only go through the one slit, on this board, he would get an image that was basically circular and real fuzzy around the edges, just kind of blurred. It was dark in the middle and just got lighter as it went out. And that was exactly what he should have got. Then he would take the 2 slits and open them. Now what that did is it allowed the light source to come through those 2 slits and then come back together and produce these interference patterns. And they would get a pattern that had bands of light and dark. This being the brightest, and then this kind of medium, and these over here the lightest. And that was exactly what they would have expected to happen. And so that didn't really cause a problem then, but a few years down the road, when we understood light better and understood that light was made up of what we call photons, the photon is kind of like the little piece of light. It's the particle of light. They redid this experiment with a proton. And they would fire a single proton, and they would cover this slit and fire the proton through that slit. And when it hit the board over here, it hit exactly where it would have, where the light beam did, the whole wave, when it came to that single slit. Then they uncovered the other slit, but they still are only firing from their proton gun, just one proton, just like one bullet. And they fire it through the same slit. You know what? It didn't go the same place. It went where the wave would have gone into one of these banded areas. Now there was what the problem was. The question for the scientist was, when they did that, how did that one proton of light, that one little bullet of light, as it approached the slit here, how did it know whether the other slit was open or not? This is a problem that scientists still have not solved. It's one of those light problems that we still don't know. And yet, it happens. The single proton knows. It's almost as if you had a gun and were firing, had 2 holes in a target down here, and if you fired the bullet through just one, it went one place, but if you ever uncovered the other hole but still shot the bullet through here, it would go a different way. You see, that's impossible. And yet, with light, it happens. Somehow that light particle knows whether that other slit is open or not. We still don't know. Nobody solved that one. There were other problems that were happening. A guy named Aristotle stated a rule, and he said, anything that is moving, a moving object, it's the natural inclination for any moving object to come to a state of rest. And you stop and think, you know that, right? Get your car going down the freeway one of these days at 60 miles an hour, and then just pop it out of gear, turn the engine off, put it in neutral, and what's going to happen? You're just going to keep on going at 60 miles an hour forever, right? I wish it were so, because gas, I could save a lot of gas. No, what's going to happen to your car? It's going to do exactly like Aristotle said. It's going to come to a state of rest. It works. Of course, all the scientists knew this was the case. The only problem was when they tried it with light, guess what? They found out just the opposite was true. They found the rule was if an object is moving in a straight line, it will continue in a straight line at that speed forever, unless something gets in its way. That totally baffled them. It shouldn't have happened. When they tested light, they were expecting it to do what? Be slowing down. It didn't. Another problem, and I'm not going to go through all of them, they found that light behaved as both a wave and a particle. It's both a wave and a particle at the same time. Now, if you look at it this way, if you have a water molecule, and that's all you got, it's just one water molecule, can that one water molecule be a wave? No. You need millions and billions of them in some body called like the Atlantic Ocean or Pacific Ocean or the Gulf of Mexico or someplace. And if you get enough of those water molecules, then you can get waves. But can one molecule be a wave? Well, common sense says absolutely not. There's no way. Problem is, it's true of light. Light behaves as particles, and it behaves as waves. And it does so at the same time. So the scientists that were doing these experiments between 1800 and 1900, they were doing experiment after experiment, and they kept getting these results. And they couldn't explain it, except they kept trying different experiments. They thought, well, the experiment must be wrong. We got to do another experiment. If we can find the right experiment, we'll be able to define light the way it should be working. And of course, every experiment they did kept coming up with the same wrong answer. Now, it turns out that that is true. Light is a wave and a particle. In 1924, Einstein and a guy named Bose theorized that the same would be true of an electron. They said electrons are particles and waves simultaneously. And on July 13th in 1995 at CU Boulder, they proved it. It was front page on the Rocky Mountain News on the 15th of July, 2 days later. It covered the whole entire front page. How is that something can be two things that can't be the same simultaneously? Well, if you're a Christian, we are posed with the same thing theologically. What are we told? God came down and was Jesus Christ, and what was he? He was all God and all man at the same time. Well, the quantum physics person doesn't have a problem with that because electrons and light does the same thing all the time. And they know it's true. It's a wave, it's all wave, and all particle, all at the same time. So the idea that God is a man and God is God doesn't really throw the quantum physics person off at all. Now this is one that really just blew my mind. Let's say we got a conveyor belt here. At this end, we're putting fruit down here. And what we got here is we got apples, the A will be apples, and we have oranges. Now, those are the only two pieces of fruit we got, okay? It's very important you understand that. Those two fruit, nothing else. They're being dumped on this conveyor belt. Here is an apple person. He's a guy standing there on the conveyor belt. You know what his job is? His job is to pull all the apples off and put them in a bin. So if he does that right, what's going to be coming down this way? Any apples? All oranges. Now down here there's an orange guy. What do you suppose his job is? Pull all the oranges off. Now, we're just talking good old common sense here. I dump all those on there. If neither one of these guys is doing anything, what's going to drop into the big bin down here at this end? Apples and oranges, right? What if I turn the apple guy on and say, all right, do your job? What's going to fall into here? Oranges. What if I turn him off and turn the orange guy on? What's going to drop in here? Well, what if I turn them both on? Nothing. All right, now, this is going to seem fairly elementary, but now we're going to have another guy. This is going to be our banana guy. Now remember, all we've got is apples and oranges going here. I'm going to put a banana guy right here. Now his job is to pull any bananas, pull them into a bin. So let's turn the apple guy on, the orange guy on, the banana guy on. What's going to fall in here? You guys are sharp. What if we put the banana guy down here? What's going to fall in there? Nothing. You guys are real sharp. Oh, here's the curve. Let me throw you this one. Let's see if you get this one right. What if I put the banana guy in between those two guys? What's going to fall in here? Nothing. Right? Good old common sense. So here comes these light guys. They're dealing with polarized light. How many of you are old enough to remember the Polaroid glasses? Okay? And if you wore them, they cut the light by about half. And the reason is because a light beam will vibrate this way. That's called horizontally. Or they can vibrate vertically. We call that being polarized vertical or being polarized horizontal. Polaroid glasses would filter out one of those. So if you put the Polaroid glasses on and the Polaroid glasses, as if you will, had a slit in it like that, then only the light going this way is going to be able to wiggle through that, right? If you got light going this way, what's going to happen? It's going to get stopped. Now, some of you remember if you had a pair of those glasses and a friend had a pair of those glasses, and you took those glasses and you put the lenses like this, nothing happened. But as you began to go like this and turn them at right angles to each other, what happened? It got black, didn't it? That's because you had this situation. Now, one of those lenses was stopping all the light going this way, and the other one was stopping all the light going this way. In other words, one was stopping the apples, one was stopping the oranges, and guess what was coming out the other end? Nothing. So, we're going to let the apple here represent the horizontal, and the oranges equal the vertical. And we're going to run this experiment again with apples and oranges, but we're going to be letting the apples and oranges be light. Now, everything works great. This guy goes on, oranges pop out here. This guy goes on, apples pop out here. If we turn them both on, nothing pops out. Now, what they did is they came up with a filter that was like this, called diagonally polarized. Now, does light do that? No. It's like throwing a banana guy in here. There isn't any. So here's the banana guy. So they put the banana guy right here, and you know what came out the other side? Nothing. So they moved him to this side, and guess what come out? Nothing. So they put him here. What are they expecting to come out this end? Nothing. You know what came out? Apples and oranges. None of the apples and oranges got pulled. They all went through. If this one was put between. Now the question is, this filter had already got the horizontal. It had been stopped right there before it ever got to this one. So how did it come out the other end? It's like, how did all those apples get out of that bin and back up on the conveyor belt? It's a problem for the scientists. You understand? That's a big problem. It doesn't make any sense. So they tried another experiment to do this, and no matter how they did it, they got the same thing. So the polarized light caused them a problem. But here was a big one. They started measuring the speed of light. Now I'm going to use some examples here too. Stuff we all know. If we have a car, I'm just going to let that circle represent the car because I'm no artiste. Okay? And this car's traveling this way. Here's car B over here. He's traveling this way. And this guy's doing 60 miles an hour. And this guy's doing 30 miles an hour. How fast is this guy moving relative to that guy? Good way to ask that question is if they hit together a head-on collision, they're going to hit at how many miles an hour? 90. Yeah, the total of both of them. So in here, we got 90. So they try this with two photons. They travel at 300,000 kilometers per second. This one's traveling the same thing. So we'll just drop these zeros and make it easy figuring. So if this guy's doing 300 this way, and this guy's doing 300 this way, then we would expect to measure what right here? 600. My problem is when you do that with light, you know what you measure? 300. But that's not the bad one. Let's try these two cars doing something else now. In the physical world we live in, if I'm in a car here going this way at 60, and you're behind me doing 60, how fast are you going relative to the other car? 0. In other words, your speed compared to the other speed is nothing. So if we calculate that, we're going to get 0. But if this is a photon car going 300, and this is another photon car going 300, and we measure the difference in speed between them, guess what we measure? Somebody out there said it. 300. Do you see where this caused problems for the scientists? Now, back in the 1800s, they didn't have cars, but they all understood this principle. Only these weren't cars. These were what? Horses, right? Same deal works, all right? You see, this is why head-on collisions are worse than tail-enders. We all know that, right? The problem is, if you're two photon cars, it don't really make any difference whether you're following the other one or coming towards them. It's the same. So this caused a big problem for these light guys. None of the experiments were turning out the way they should. This happened from 1803 all the way up to 1905. 1905, things changed. You know why they changed? You had a little 26-year-old kid who was so bad at math he couldn't even balance his own checkbook. Serious. His wife had to do the books because he would get them all screwed up because he couldn't do add and subtract, just threw him for a loop. He was 26 years old. Anybody know what his name was? Albert Einstein. Albert Einstein figured, we've been doing experiments for 102 years. We've got thousands of experiments. They all keep coming up the same. Albert Einstein was a bright boy. Maybe he couldn't do add and subtract, but he understood one thing. We've probably done enough experiments. We got 102 years of experiments that all say the same thing. In 1905, Albert Einstein did something that up until that point, no scientist had done. And it wasn't do another experiment. He sat down and he asked a question about those 100 years of experiments. And the question was simply this: what if those experiments are right? Nobody had ever done that before. They were all convinced the experiments were wrong. They're trying to make the experiments work. Einstein says, we've done enough. Maybe they're right. Maybe what's wrong is our common sense is messed up. Maybe our common sense is wrong. So Einstein decided, since we can't argue with what is the experimental evidence, then our common sense must be wrong. So Einstein sat down and, using the evidence of the experiments, sat down in a chair and went off into La La Land, literally. He was a very visual person. And he says, what would the universe look like if those experiments are correct? Closed his eyes. He tells how he literally pictured, and according to these rules, a beam of light had to curve, for instance, and he could see the light curving in his mind. So he got a picture of the universe based on the evidence. Evidence about things on the subatomic level. Not on the level we live at, but at subatomic. In other words, that means based on what's going on with the particles that actually make up atoms. What's going on at that level? He pictured a universe. And then, because he wasn't real good at doing the actual number crunching, he got his wife, who happened to have a doctorate in mathematics, and says, sweetheart, I got some ideas here, jot this down. And what they basically were doing is they were going to sit down and define the mathematical laws to define the universe that the experiments had defined. Did that make sense? They were going to define the mathematical laws that would define the universe as defined by the experimental evidence. And that's what they did. In 1905, he published it. It became known as Einstein's special theory of relativity. The only problem was he hadn't included the effects of gravity. And so he said, we really need to redo this work and include the effect of gravity, how gravity plays into this thing. So in 1916, 11 years later, published another paper called The General theory of relativity. And the world has never been the same since. It's never been the same. In those papers, there were some very interesting things that I want to look at. There was a lot of stuff in there, but I want to look at a couple of them. He talked about what happens at the speed of light. If something begins to accelerate, so you have, let's say, a spaceship, and the spaceship is that long, and it's heading this way, as it moves faster and faster and faster, the length of the spaceship as you approach the speed of light gets shorter. And you know how short it actually gets at the speed of light? Disappears. The length at the speed of light goes to zero. This is why Einstein said it's impossible to travel at the speed of light, because at the speed of light you cease to exist. Your length goes to zero, and you're gone. But here is where it gets goofy. Does everybody know what mass is? In other words, I'm more massive than a newborn baby. Mass is the stuff, if you subject it to gravity, it produces weight. It's the stuff. Okay, the stuff we're made out of. Now, as you approach the speed of light, and you have this much mass, as you come up to the speed of light, you know what happens to your mass? Yeah, it goes like that. Wrong. It goes like that. You know what happens at the speed of light? It becomes infinitely large. Now, the scientists, you see why this was causing them an issue? Normally, you would say, how can something get smaller and smaller and smaller, and yet its mass get bigger and bigger and bigger? And yet, that's exactly what happens. This stuff has all been proven experimentally now. So the mass increases until at the speed of light, it's infinitely big. Its length goes to zero. Another thing about time, if you had a clock on your spaceship, guess what happens to the clock as you start going faster and faster and faster and approach the speed of light? Good. It slows down. Do you know what happens at the speed of light? It stops. It stops. Einstein produced what he called a thought experiment, and he said, we have two twins. And I happen to have two twins in my family, Katie and Travis. And so let's suppose Travis, since he likes airplanes, she likes horses. She likes terra firma, riding on her horse, you know. Travis wants to fly airplanes, and if he could get a chance to be in a spaceship and go to another planet, he would do that tomorrow, right? So Einstein would say, okay, we got these two twins. One of them gets in a spaceship and flies to Alpha Centauri. Now, Alpha Centauri is 4.5 light years away. Now, what does that mean? It just means that the light, when you look at Alpha Centauri, the star, the light you see left there 4.5 years ago. Took the light 4.5 years to get here. That means it's 4.5 light years away. That's what a light year is. The distance light travels in 1 year. So, he gets up, he very quickly accelerates to 99.9% of the speed of light. Now, why does he not accelerate to 100% of the speed of light? Because the experiment just goes away at that point, doesn't it? It's like, he's gone. Where'd he go? So he goes to 99.9% of the speed of light, flies to Alpha Centauri. What's happening to his clock? Slowing almost to nothing. What's happened to Katie's clock? Just ticking right on, right? So when he gets to Alpha Centauri, he gets there, and it's just about time for him to dig into his sack lunch. So he walks across the Alpha Centauri grass and crawls up under an Alpha Centauri tree, eats his lunch, walks back across the Alpha Centauri grass, gets back in his spaceship, and he heads back to Earth at 99.9% of the speed of light. And he gets back to Earth just in time for supper, which Katie has very nicely prepared for him. The only problem is, since he took off, she waited 9 years before preparing that supper. He's been gone a day. She's 9 years older. So we homeschool, and they were studying galaxies and all this. And I go in and I say, I think I was talking to Katie, and I said, what's it say there about that star? How far away is it? She said, 1,000,000 light years. Now, we've taught them, of course, that the universe was created by God 6,000 years ago. We believe in that. The whole universe, God popped into existence 6,000 years ago. So I said to her, and we get into this on dinosaurs. Where are the dinosaurs? Do any of you know where the dinosaurs went? Anybody know where the dinosaurs went? Nowhere. They're still here. They're still here. Well, we call them lizards and things like that. You know, a reptile never quits growing. Never quits growing. How long did people live prior to the flood? Like 900 years. Like 10, 11 times. If a reptile, you take one of these great big kimono lizards, if he were to grow 12 times the size he is, how big would he be? He wouldn't fit in this room, and we'd call him a what? Dinosaur. They didn't go anywhere. They're called turtles, lizards, snakes. They're still here. So anyway, we've taught them. All that was done 6,000 years ago. So I says, is that true? Is it true that that light's been traveling from that star for 1,000,000 years? No. Well, why not? Because that galaxy was only created 6,000 years ago. So I said, so the light couldn't possibly have been coming from that star for 1,000,000 years, right? She says, right. This is wrong. She says, well, how long has it been coming? I says, it's been traveling from that star for 1,000,000 years. That's a true statement. How long ago was that star created? 6,000 years ago. This is another one of those things about light that works but doesn't work. Okay, both of those are true statements. The star was created by God 6,000 years ago, and the light's been traveling for 1,000,000 years. And there are galaxies out there where the light has been traveling billions, with a B, billions of years. And you know when they were created? 6,000 years ago. Boy, this plays havoc on the evolutionists. So how does that work? What happens to time at the speed of light? Stops. So the light you're seeing today, measured by our clock here on Earth, remember Katie's clock, the 9-year clock? As measured by that clock, that stuff has been traveling from that star for how long? 1,000,000 years. But from the light beam's perspective, Travis's, by his clock, by the clock on the light beam, how long ago did it leave that star? Just an instant. Because at the speed it's traveling, there is no time. How do you like that one? Einstein said it's all relative, guys. It all depends on where you're standing. I did a little thing with Sam the other day in the car. I said, we're going down the road at 45 miles an hour, and I said, if somebody's standing over there on that hill of dirt, and you ask them, how fast is Ken going? They're going to say, what? 45 miles an hour, right? But if I ask you, how fast am I traveling, what are you going to tell me? Nothing. Compared to you, I'm not traveling anywhere. We're sitting in this seat, and we're stationary, one to the other. But to that guy on the hill, I'm moving 45 miles an hour. See, it actually happens in the real world, too. It all depends on your perspective on things. Einstein came up with a formula. E equals mc squared. If I said to you, water equals, that represents ice cubes, and that would say 12. 12 ice cubes equals water. Is that a true statement? Sure it is. But what if I take away the multiplier? Ice cubes is water? Does that work? Okay. I'm just giving you a couple real world examples here before I lay the real one on you. What if I put something up here and I said, egg salad equals eggs 12. That could be true, right? Does it change anything does egg salad equal eggs? Sure it is. Many of you have seen this formula, but you don't understand the power of it. The c is the speed of light squared. It's like the 12 in the other examples. It's a multiplier. Doesn't mean anything. You can get rid of it. Now, there's the essence of the formula. What's the E stand for? Anybody know? Energy. What's the M stand for? What does that formula say about energy and mass? Same thing. Now, back in Einstein's day, he was just this was theory. You know, it's not theory anymore. We now know something. We now know that all those particles that make up atoms, and most of you were taught in school that we have protons, neutrons, and electrons, right? Well, folks, things have changed. All those little particles that make up atoms, protons, the neutrons, the electrons, the muons, the mesons, the leptons, the bosons, the baryons, the gravitons, the sleptons, the neutrinos, the fermions, the hadrons, the quarks, the gluons, etc., and etc., etc. Oh, yes, even the one called the oh my God particle. Really, that's what it's called. I'm sorry. They are all energy. Now, you heard me say that, but I don't know if you really heard me. I want to be very clear you understand. I did not say they are made of energy. I said what? They are energy. Energy and mass, the same thing. There is no mass in the universe. On the subatomic level, there is no mass. It's all energy. Your body is all made of energy. We are energy beings. That gets important here in a minute. We're all energy beings. There is no mass. It's all energy. In fact, on the subatomic level, you will find that when they measure mass, they measure it. What's its mass? They say, well, it's so many electron volts. Electron volts is what we measure energy with. So they actually measure mass in the unit of energy. They literally do that. Looking at atoms, what is an atom? Now, we were taught that you had a nucleus, right, made of protons and neutrons. You had your little electrons floating around outside, right? Well, if that's what you think, check with your youngins in school, because they'll tell you that that ain't the way it is, Mom, Dad. Sorry. Because we now know that that's not the way it is. Oh, and by the way, using that model, if you create a nucleus, and here's your little atom, and you made that nucleus of protons and neutrons the size of a grain of salt. You with me so far? Size of a grain of salt. On that scale, how big would the electron be? The size of a dust particle. And you know how big that atom would measure from here to here? 14 stories. At 10 feet per story, that's 140 feet in diameter if you blew it up that way. So you'd have this thing that's 140 feet across, a dust particle out there, and a grain of salt in the middle, and that's an atom. Some of you heard people say that atoms are basically space. Well, that's why. But unfortunately, that's not the way it is. Because electrons are standing waves form an electron cloud. Electron clouds are like wave functions, and wave functions are mathematical concepts. Now, I know what you're saying. Could you put that in English, please? So let me try and explain it, all of that. What it basically boils down to is that electrons don't really exist. They are a probability function. Let me try and explain what we mean by that. A probability is when you have a chance of something happening. One of the experiments they used to do is the dead cat experiment. They said, you got a box that has a cat in it. Is the cat dead or is it alive? Well, it could be either, right? We don't know. We have to do what? Open the box. So you have a probability function going there. You have a 50-50 chance. You know what happens the minute you open the box? The probability function collapses because the cat is either going to be dead or alive. If it's dead, now you have a 100% chance of dead, 0 of alive. If it's alive, you have 100% of alive and 0 dead. The 50-50 probability function collapses on itself mathematically. So we don't really know where the electrons are. We just know that there's a certain probability that it's there. But we really don't know. So we don't have anything, just quanta, and that's where the term quantum theory comes from. It's just quanta means probability. So the whole universe is based on mathematical probability functions. This is the math of this stuff. Remember we talked about the probability functions collapsing? Here's the problem we have on the light level. Since light is energy, and all the little particles in the atom are energy, what do we have to have in order to see something? Light. And we see it via reflected light, right? But what happens when you put a photon of light and you hit a part of an atom with it? It changes the atom. The atom takes on energy, gives off energy. It's no longer what you were trying to see. So the very act of observing changes what is being observed. It messes it up. I'm not going to get into all the stuff because, quite frankly, I tried to figure out where they're going on this, and it's beyond me. But you jump to the end of the book, and after they go through all the stuff, and where they take this probability problem, when they take it to its logical conclusion, what do they end up with? They end up with this very simple fact. The universe can only exist if it is being observed. The universe has to be being observed in order to exist. Well, this is where we started getting things like, if a tree falls in the forest and there's nobody there to hear it, does it make a sound? Does it? How do you know? Yeah, but once you put a microphone there, then you are observing it. And of course, it's going to make a sound. It only makes a sound when observed. Nobody knows whether it makes a sound and can prove empirically that it actually makes a sound when it's not being observed. Because you see, the very act of observing it changes it, doesn't it? Changes the rules. The thing is does it make a sound when not being observed? The only way to determine that is to do what? Observe it. Now it's no longer not being observed. Do you see the problem we run into? Only the problem is it's bigger than that. We're not talking about a tree in a forest. We're talking about the entire universe. Those stars that are billions of light years out there, and even stars we haven't even seen yet, none of them can exist unless they're being observed. The question is then, who's observing it? Who is observing it? And you know what a lot of the quantum physics guys come up with? A creator God. Now, do all of them come up with that? Nope. You got some guys, like Carl Sagan, with his billions and billions and billions of stuff out there. His basic idea is this: the universe is circular, thus negating the existence of a creator God. He was an atheist. Now, get my words there. This is none of those light paradoxes. The universe is circular. Thus, in Carl Sagan's mind, it negates the existence of a creator God. Other non-atheistic quantum physics guys make this statement: the universe is circular, thus proving the existence of a creator God. Aha! Are we going 45 or 0? The facts are the same, but your point of reference can change everything, can't it? Carl Sagan came at it from an atheistic viewpoint, so he interprets it one way. Those who believe in a creator God interpret it another way. Now, within those that interpret it as a creator God, which is the vast majority of them, there's two views of that. You have those that say it proves the existence of a creator God. Those are guys we would call pantheists. These are the people, you ask them, who's God? And they say Gaia, or whatever it is, Mother Earth. They believe in a creator God. They believe the universe was created in an instant by a creator God. There are others, like the gentleman that I read to you at first. He would say it proves the existence of the creator God, big G. Okay, that's the difference that exists within the creator God group. Guess what most of them tend to be? They're a people, a creator God, Mother Earth, whoever, the force. May the force be with you. The force did it. How many of you know who Stephen Hawking is? Very famous mathematician. When you put Einstein's mathematic ability up against Stephen Hawking's mathematic ability, Einstein loses. This man is a mathematical genius. I want to read you something that he says. Now, this guy may be a Christian, so listen through the whole thing, because you got to get to the last word before it makes sense. So long as the universe had a beginning, we would suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, which it seems that that is the case, it would have neither beginning nor end. It would simply be. What place, then, for a creator? He goes on to say, however, if we do discover a complete theory, then we would know the mind of God. Boy, that's a heavy, 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 heavy statement. That's from Stephen Hawking. Now let's go back to Genesis 1. We're going to look at these verses now from the view of the quantum physicist. And God said, let there be light, and there was light. And God saw the light, that it was good, and God divided the light from the darkness. Now the two words I want to focus on there is the word said in verse 3, and God said, and in verse 4, and God saw. Go home, look that up in your Strong's Concordance. It will define the word said and saw just the way you think and have always been taught it is, but it will also say it could just as easily have been translated this. The word said could be translated to say in one's heart, to think, to intend. Does any of that imply a verbal voice? Matter of fact, if you're saying in your heart to think, you're thinking or intending, where is that all taking place? Between your ears, right? When you think, where's your thinking processes? The word saw could just as easily have been translated to perceive or have vision. Now, where is your perception and vision take place? Right up there, right? Why did the translators interpret it in a voice type thing? Well, maybe they didn't even have any idea of what we've been talking about here tonight. Is that possible? So they had to go with what made sense. Those two verbs can be translated either way. So you go with the one that makes the most sense. But in the light of quantum physics, the verbal one doesn't make sense. It's only the thinking one that makes sense to a quantum physicist. Now, when you start thinking about that, in Colossians 1, verse 16, it says, for by him were all things created that are in heaven and that are in the earth, visible and invisible, whether they be thrones, dominions, principalities, powers, or all things were created by him, for him, and he's before all things, by him all things consist. Now let's just hold that real quick. And if God's doing the observing, how is he doing it? The quantum physicists would say this. It's like an author. If I author a book and I have a story, I like to use Centennial. If any of you ever seen that, Centennial goes over like 4 or 5 generations. If I write that story, you got a character in the story. That character can only exist where? At that moment of action in that story, right? If you got a character, and this book goes from 1700 to 1900, and you got a characters in 1700, he can only exist in that 1700 context, can he? He can't exist in that story 200 years later, can he? He's got to exist in his predefined point. Okay, so from that end. Where does the author exist in the story? From the beginning to the end. The whole story is right there, all simultaneously. He exists throughout the story. But get this. Does the author exist before the beginning of the story? Sure he does. That's why they go back sometimes, like in Star Wars. The guy went back, did what? 3 prequels. He had a pre-story. Do most authors have in their mind what's going to happen after? You bet they are, because if the story goes really good, like Left Behind, they wrote a book, it went over really well, so what did they do? They kept going, right? So the author of a book exists from the beginning to the end, before the beginning and after the end. God writes the story in his mind. It's the universe. He's got the whole thing. Where does he exist in the story? From eternity past to eternity future. He exists throughout because it's all right there. He's got it all right there. You know the only difference in God's story and an author's story is God's able to do something with his characters that no author, no human author can do. God was able to write his story and yet give his characters free will to determine what their part in the story was going to be. and yet still exist across the whole timeline of the story. Do you begin to see where all of a sudden we say, how can God be all omniscient? That means omniscience. How can he know everything? Well, he's the author. How can he be omnipresent? How can he exist throughout time? He's the author. He's omnipotent, all-powerful. Man, if I'm writing the story, do those characters have any power over me? I'm going to write that thing the way I want, right? I got all the power in the world in that story, right? He's the author. You see how it explains a lot? Remember the guy said at the beginning, I see this stuff and I say, wow, so that's how God did it. Remember the Tower of Babel? They were building a tower to heaven. I'm going to tell you something you may not believe, but it's true. There is evidence, archaeological evidence, all over the place. A guy wrote a book called Chariot of the Gods. There's archaeological evidence, stuff dug up that happened thousands of years ago where they got dry cell batteries, they got spacemen, they got all this stuff. Folks, you can only explain that two ways. Either there's extraterrestrial life out there, or sometime in Earth's past, we had a very technological society that existed here on Earth. I firmly believe that before the flood, people were flying into space. They were doing everything we're doing today. Noah lived in a world very much like the one we live in today. He wasn't running around trying to start a fire by striking two sticks together. He just turned the burner on, just like you do. So Tower of Babel is shortly after the flood, and these guys are building this tower. If you look at it, what they're doing is they're messing around with the mind of God. And this is a tower of learning. It's a scientific center that they're building. And what does God say? I got to stop them because nothing they set their mind to will they not be able to do. They're going to be able to do whatever they want. So what were they doing? They were taking their science and they were marching right into God's front yard. And God said, close enough, folks, close enough. I will tell you this. I think with quantum physics, we've marched right through the front yard and we've opened the door and marched right into his front room. So how long is it going to be? You see, when you start talking about it's close to the end, it may be there in more ways than one. Some other strange things. These subatomic particles all have angular momentum. You know what angular momentum is? That's like when you spin a top. If I have a little top this big and a merry-go-round, which one do you think has the most angular momentum? The big one. The bigger, the more angular momentum. To have angular momentum, it's got to be spinning. All these electronic particles have angular momentum. The only problem is nothing's spinning. How do you like that? Here's an experiment they did. They started out with two little photons. They put a spin on one of them of a certain amount, and they put another spin on this one, so that one's spinning this way and one's spinning in the opposite direction. And then they shot them in opposite directions. Over here, they set up a magnetic field that caused this one to spin off like that. Do you know what this one over here did the very instant that one made that turn? This photon over here went ting, with nothing anywhere near it. Again, telepathy again, you know, how did this photon know what was going on with that photon? Again, you see similar to the one I did at the beginning? Nobody knows. We have no clue. Well, we know it happens. What might we be able to do with this? Instantaneous communications, because believe it or not, that doesn't happen at the speed of light. It happens instantaneous. I remember in 1994, I went to a thing put on by IBM for their employees where they were getting us all prepared for the future, and the guy was telling us all this stuff. And I raised my hand and I said, man, it sounds a lot like Star Trek. He says, yeah, you know the only mistake Gene Roddenberry made with Star Trek? He put it about 200 years too far in the future. Listen to this article. This is from the National Geographic. This was April 18th, this year. National Geographic News. It sounds like something out of Star Trek. Austrian researchers have teleported protons, particles alike, across the Danube River in Vienna using technology that calls to Scotty beaming up Captain Kirk. We were able to perform a quantum teleportation experiment for the first time ever outside the university laboratory, says this guy. Researchers read the blueprints of the photons they wanted to teleport. Then they broke up the photons into smaller particles called quantum bits and sent these bits along with the blueprints through the fiber optic cable in a sewage pipeline under the river. If you know anything about Star Trek, you know that's how the teleporter works. At the other end, replicas of original photons were created, The original photons ceased to exist only once the replicas were created. Transporting of mass. You say, yeah, but the photons are energy. Yeah, but energy and mass, same thing, right? Now, one last thing. I like to end with this always. Einstein proved that energy equals mass. He also made another statement. He said space equals time. We now know that to be true. Okay? Space and time are the same thing, just like energy and mass are. Let's look at the omnipresence of God in that light. If this is true, we've all been taught that God is what? Omnipresent. What does that mean? Is God here tonight? Sure. Is he in China? In a church in China tonight? Sure. If there was a church on the moon, would he be there? Sure. God is everywhere, isn't he? That's this. But this is equal to time. So if God is everywhere, then he's also every when. The verse in 2 Peter 3:8, but beloved, be not ignorant of this one thing, that one day is with the Lord 1,000 years, and 1,000 years is a day. Most often that's interpreted as a day with the Lord is 1,000 years. I don't think there's anything necessarily wrong with doing that, but that's not what that verse is saying if you look at the English. It's the reverse. 2 is 1, 1 is 2. What is it saying? It's saying basically that with God, there is no such thing as time. Why? Because he is every when. I always marveled at this verse, but God commendeth his love toward us in that while we were yet sinners, Christ died for us. Wow. Isn't that neat? While I was yet a sinner in the year 2004, Christ died for me 2,000 years ago. How could he do that? Because he's every when. From God's perspective, when is the crucifixion taking place? Right now. When is the creation taking place? Right now. When's the great white throne judgment taking place? Right now. Do you see how God could speak to his prophets and say, you tell the people this is going to happen? Because he was already there. He was there. It was happening. He saw it happening. Everything is happening now to God because he exists across time, from eternity past to eternity future. Plus, he's everywhere at every given instant. Wow. You know why? How can you do that? He's the author. He's the author of the whole story. And you know what it all boils down to? We like to put God in a box constructed by our common sense. And you know something? God can't be put in a box. And you want to know something else? God will not be put in a box. So you can go ahead with your common sense and try and define what you think God is and what he expects of you. But you know, on the basis of what I've just gone through tonight, the only thing you can say is, we serve an awesome God. And you can understand that awesomeness for the first time in human history. Through our modern science, we get a glimpse of just how awesome God is. Nothing can exist unless he's observing it. You know what that means? Does he care about you? Does he care about sinners? Yes. You know how we know? Because we exist. If God ever quit thinking about us, we would cease to exist, and not just now. We would disappear from the timeline just like Jimmy Stewart does in It's a Wonderful Life. We would never exist, ever. The world would be a different place if God were to quit thinking. So, taking it to the extreme, did God care about Hitler? Yeah, you know how we know? He existed. God could have just quit thinking about him and everything would have been changed. But he didn't, because he cared.